Meta has introduced SeamlessM4T, a revolutionary unified system that supports a wide range of translation tasks. To create SeamlessM4T, the authors embarked on an ambitious journey. They leveraged a staggering 1 million hours of open source audio data to develop self-supervised speech representations using WTV-BERT 2.0. Next, they curated a multimodal corpus named SeamlessAlign with over 420,000 hours of automatically aligned speech translations. This resource was then combined with human-labeled and pseudo-labeled data, totaling 406,000 hours. The results are nothing short of astounding.
The technology is multimodal. That means that it can understand language from speech or text and generate translations into either or both. It can also transcribe speech into text, and all with a single model. What's very exciting is that it's also massively multilingual. Right now, it supports translation into nearly 100 languages for text and 35 languages for speech.
SeamlessM4T Large, the larger model of the two releases, outperformed the previous state-of-the-art S2ST model, or Audio Palm 2 8 Bast, by a remarkable 4.2 BLEU points when translating into English. Compared to cascaded models, SeamlessM4T Large boosts translation accuracy by more than 2 BLEU points. When translating from English, it surpasses the previous state-of-the-art XLSR 2B S2T by 2.8 BLEU points on Covost 2. Research tells us that speech-based communication fosters stronger social bonds between individuals. It's not just about conveying information, it's about building relationships. Moreover, speech is often the most practical and accessible form of communication, making this innovation more impactful. Before unified speech translation models emerged, much of the focus was on cascaded approaches. This involved chaining subsystems for tasks like ASR, T2TT, and TTS. While cascaded systems benefit from specialized advancements in each subsystem, they do have limitations. For instance, a two-stage cascaded S2TT system involving ASR and T2TT doesn't match the quality of a single large-scale T2TT model. When you look at OpenAI's Whisper, a massive model designed for translations in English, what sets Whisper apart is its multitasking prowess. Whisper demonstrates that scaling weakly supervised pre-training can achieve exceptional ASR, or automatic speech recognition, and S2TT, speech-to-text translation, results without the need for self-supervision or self-training techniques. Whisper's power lies in its extensive training data. It's been trained on a whopping 680,000 hours of data. This extensive training has allowed Whisper to achieve state-of-the-art translation quality in an impressive 82 FLIR's languages translated in English. However, it's essential to note that its performance is currently reported for translating into English only. Throughout this paper, the models are rigorously evaluated using several key datasets, each designed to assess specific translation aspects. These datasets include Flores 200, a multilingual translation benchmark, Flores, which covers speech and text in 102 languages, and Covost 2, a large-scale S2TT corpus, and CVSS, designed for multilingual speech-to-speech translation and text-based semantic accuracy evaluation. Developing a versatile system like SeamlessM4T necessitates vast resources spanning numerous languages and modalities. Enter parallel data mining, an alternative to closed data sources that provides broader language coverage and larger corpuses. The key approach here is encoding sentences from various languages and modalities into a shared fixed-sized embedding space. This space helps identify parallel instances based on similarity metrics. One crucial component in this journey is language identification, or LID. It's the process of identifying the language of raw audio data, a critical step for a multilingual system like SeamlessM4T. While off-the-shelf LID models exist, none covered the target list of 100 languages. So the researchers developed their own model based on the eKappa TDNN architecture. And training on a robust LID model involves a series of steps. First, they retrain a system from scratch on Vox Lingua 107 data to establish a baseline. With the pipeline validated, they trained the model for 40 epochs, requiring approximately 172 hours on 8 GPUs. In total, 17 hours of speech data was used, with an average of 171 hours per language, spanning from 1 to 600 hours. The F1 scores on the test data reveal the model's performance. Interestingly, training on additional languages slightly decreased the overall performance for common languages. This is due to the presence of closely related languages. Maintaining high-quality LID labeling is crucial. Depending on the available data quality for a specific language, filtering may be necessary to retain high-quality data. In one instance, by rejecting 8% of the data, the researchers were able to boost F1 measure by almost 3%. And when it comes to audio, the researchers began with a staggering 4 million hours of raw audio sourced from publicly available web data. To enhance the quality of mined pairs, they opted for an over-segmentation approach. First, they used an Open Voice Activity Detect, or VAD, model to split audio files into shorter segments. Next, their speech-language identification model came into play. Analyzing each segment, finally they created multiple overlapping splits for each segment, letting the mining algorithm select the optimal split. With the ground source laid, the next step was training encoders for both text and speech. These encoders were then employed to project modalities into unified embedding space. Mining speech segments against text sentences or speech segments in other languages yielded a treasure trove of S2TT and S2ST pairs. These rich corpora were combined with other resources to train the SeamlessM4T model. Introducing Sonar, a novel sentence embedding space that's both multimodal and language agnostic. Sonar takes the stage as a significant improvement over the previous laser space. Much like its predecessor, Sonar follows a two-step approach. First, it trains a text embedding space and then leverages a teacher-student training strategy to extend its capabilities to speech modality. Speech encoders play a pivotal role in S2TT and S2ST mining. The results are fed into the SeamlessM4T system, but evaluating these encoders is no small feat. While a comprehensive evaluation would involve extensive computing power, the Sonar embedding space comes with a text decoder, allowing for a S2TT evaluation. Remarkably, even a zero-shot scenario, the Sonar speech encoders hold their own against formidable models like Whisper Large V2. One of the grand goals of SeamlessM4T is to bridge the gap between direct and cascaded models for S2TT in vast multilingual and multimodal settings. The mission is to create a robust direct X2T model for translating both text and speech into text. By combining powerful speech representation learning with a massive multilingual T2TT model, this paves the way for speech-to-speech translation through Unity, a two-pass framework that predicts both text and discrete acoustic units. The building blocks of SeamlessM4T involve GVQ codebooks, a critical element for masked prediction learning, and RPQ, a unique addition to enhance the model's capabilities. These components contribute to the training process with their corresponding loss function denoted as LMGVQ and LMRPQ. At the heart of SeamlessM4T Large lies the W2V BERT 2.0 pre-trained speech encoder, following the W2V BERT XL architecture. The powerhouse boasts 24 conformer layers and a staggering 600 million model parameters. It's been meticulously trained on a vast dataset comprised of 1 million hours of open speech audio spanning 143 languages. Unity, the multitask framework at SeamlessM4T's core, revolves around the X2T model, a multi-encoder speech-to-sequence masterpiece. The model features a conformer-based encoder for speech input and a transformer-based encoder for text input, both united by the same text encoder. It's trained on S2TT S2TT data, pairing speech audio from a source language with text in target language. To gauge the source of S2TT and S2ST, the authors extended the evaluation beyond traditional automatic metrics. They introduced Blazor 2.0, a modality-agnostic metric that assesses quality in both speech and text. Blazor 2.0 supports a multitude of languages in both speech and text, fostering an extensive evaluation process. In the realm of S2TT evaluation, two protocols were employed: XSTS for translation quality and MOS, mean opinion score, to assess naturalness. The results as revealed through XSTS protocol demonstrated SeamlessM4T large consistently achieving high quality scores by translating into English and from English into various languages. A replicable noise-robust evaluation benchmark was crafted, aptly named Noisy Flurs. This benchmark covers a staggering 102 languages, features 2 speech tasks, and incorporates various noise types, including natural sounds and music. Through blue SNR curves, S2TT and WERSNR curves, or ASR, showcases impressive resilience in high-resource languages, consistently outperforming Whisper Large V2 by significant margins. To understand the presence of added toxicity, we turn to two pivotal datasets, FLIRS and the Holistic Bias Framework. The focus here is to align with human evaluation efforts and other evaluative components of the work. They meticulously evaluated the output of SeamlessM4T large on FLIRS dataset. The results revealed valuable insights. Overall, FLIRS demonstrates a respectively low prevalence of added toxicity, averaging at a mere 0.15% across languages and tasks. In specific scenarios such as S2TT and S2ST, they observed slight variations in added toxicity levels compared to FLIRS, notably high in S2TT and slightly lower in S2ST. Now, let's shift our focus to remarkable advancement in multimodal translation achieved through SeamlessM4T. Here we fuse 4 key building blocks, including the massively multilingual 2TT model, WTV BERT 2.0, speech representation model, and T2W text-to-unit speech-to-sequence model, and Hi-Fi GAN, a multilingual vocoder. The fusion of these elements has resulted in a unified model that expands language coverage and translation directions exponentially. SeamlessM4T now empowers us to perform translations from English to a remarkable 35 languages and vice versa, alongside covering S2ST from 100 languages to English.
There's a second trend I want to share with you, which relates to why AI isn't more widely adopted yet. It feels like a bunch of us have been talking about AI for like 15 years or something. But if you look at where the value of AI is today, a lot of it is still very concentrated in consumer software internet, right? Once you go outside, tech or consumer software internet, there's some AI adoption, but it all feels very early. So why is that? It turns out if you were to take all current and potential AI projects and sort them in decreasing order of value, then to the left of this curve, the head of this curve, are the multi-billion-dollar projects like advertising or web search or for e-commerce, product recommendations, or a company like Amazon. And it turns out that about 10, 15 years ago, various of my friends and I, we figured out a recipe for how to hire, say, 100 engineers to write one piece of software to serve more relevant ads and apply that one piece of software to 1 billion users and generate massive financial value. So that works. But once you go outside consumer software internet, hardly anyone has 100 million or 1 billion users that you can write and apply one piece of software to.